In this video, I will show you how to perform a three-dimensional current density simulation from this Kicad layout of an Arduino Uno board. Let's simply start. I shared the folder with all the project files in the description. Let's open the Kicad layout. You must use the same Kicad version as I did. Now also open FreeCad 0.21.2. Please also use the same version as me. To load the 3D model of the ground plane, copy this script into the Python console of FreeCad and hit enter to execute the command. If you cannot see the Python console, please follow these steps. You will need to have FCAD PCB for this step. Check out this GitHub link for that. But at least one of my Udemy students had problems to use the FCAD PCB from GitHub, so I uploaded my version of FCAD PCB into this folder. Copy the FCAD PCB folder into the macro folder of FreeCAD. Once it is finished, I will make the PCB invisible and rename the ground plane to GND. The Arduino board is powered via this USB socket, so this pin will later be our ground pin. As we have a power connector here, and a standard USB socket can only deliver 500 mA, I will later set up the simulation so each of the pins draws 200 mA, which would be relatively realistic. At the end of the video, you will be able to also set up the current draw of the other components. I will generate some pads manually. For this, click on the ground plane, go to the part design workbench, and create the body. Click on the top face of the ground plane and create a sketch on it. I will simply draw all the pads the same size, so we later have an easier time to calculate the current density. Once you're finished drawing the injection pads, click on Close. Now let's extrude these pads by, let's say, 100 micrometers. Now export the ground plane as STL file. Sadly, the FCAD PCB macro has still some bugs and creates shapes that self-intersect. In order to clean up the shape, I will import it into Meshlab. Use the Merge Vertices tool and reduce the vertices to 0.03, which corresponds to 30 micrometers. I chose this value as it is a bit less than our 35 micrometers of copper thickness. Now export the mesh. I will call the new file like this. Open it in FreeCAD. Now perform these 3 steps. Save the refined shape as brep file. I chose brep as it is the fastest file format for meshing. Anyway, all the other major file formats would also work. In my previous video regarding 3D simulation, I opened the file with the Gmsh GUI. Sadly, as this model is much bigger, the GUI will be super laggy. Hence this time we will create the mesh via the command line. For this I created this file and placed it into the same folder as our 3D model. Simply open it with a text editor. It only has 4 lines. The first line is just an init command and will always be the same for this kind of simulations. The second line defines the file that we want to convert. The next 2 lines are the meshing algorithms. I chose them as they worked very reliably for many different copper shapes. The 5th line is just a comment, but I use it as a place to store the command that we have to type into the command line in a bit. Open the command line and change the directory to where we save the brep file. I just copy the path from the Explorer window and add a cd in front of the path. Cd means change directory. This command will now execute the .go file. The CL scale option can be used to define the fineness of the mesh. 1 would be the least fine mesh. I set the fineness to 0.1, which is 10 times finer than the standard value. The -3 at the end tells Gmsh to store a 3-dimensional mesh. The meshing should start now. If it doesn't, you might have an issue with the Gmsh installation. You can test out if Gmsh is properly installed by just typing Gmsh in the command line. After waiting for a few minutes, a .mesh file has been created. The next step is to create the simulation file of the mesh file. We now have the same problem that the mesh is so big that the graphical user interface of our simulation tool Elmer is super laggy. So I will again perform the simulation via the command line. To do this, create a new folder called Elmer. Create 2 text files. The first one we call case.sif and the second one elmersolver_start_info. Open both with a text editor. The case.sif file has quite a few lines, so best copy it from the link that I provided. We will only change the boundary condition starting from line 6.8. Each boundary condition only has 3 values. We can define a name to it. Then for the ground pad we can set the potential to 0 volts, and the boundary conditions are basically the phases. We will search them in FreeCad. Open FreeCad. When you click a phase, you can see the corresponding phase number in the Python console. I will only select one phase for this demonstration. Here you have to insert the number of phases. The number here should be equal to the number of phases that you applied. Let's now mark the phase of the current source. We sadly cannot define a current, but instead we have to apply a surface current density. I calculated via this Excel sheet. Save the zip file and let's now start the simulation. Change to the Elmer directory in the command line. Let's make a short check if you have installed Elmer correctly. For this, type Elmer GUI into the command line. This command should open Elmer GUI. If this worked for you, you're ready to go. Now close the Elmer GUI window, as we will do the rest in the command line. This command converts the mesh file into the file format that Elmer needs. I got the commands from the Elmer grid manual. .14 is the source file format. In this case it's a mesh file. And 2 means that we convert it into Elmer file. This is the name of our source file. Now hit enter in the command line. This folder should now have been created. Move the case.zip file and the Elmer solver _start_info into the created folder. Now back in the command line, change to the newly created folder as well. Type Elmer solver and hit enter. Now this VTU file was created. This file stores the simulation results. You can open them via ParaView in the common graphical user interface, like this. Or open it via the command line by typing ParaView plus the file name. You can change between the voltage view and the current density view here. Here you can change the display range. As this video is quite long already, I will stop recording now. In part 2, I will show you how to add the PCB and the other copper traces to the view.